We're now going to talk about the next pattern in our pattern sequence, which is the builder pattern. In this discussion, you'll help to understand how the builder pattern works, how it's composed, how it's implemented, and you'll also get a chance to recognize how the builder pattern can be applied to incrementally build an expression tree from a parse tree. The purpose of the builder pattern is to recursively build the expression tree's composite-based internal data structure from the interpreter-generated parse tree. There will be many classes in this design, but only a handful of patterns, which helps to reduce the surface area you have to worry about as an application developer. Let's start by discussing the context of how this pattern can be applied for our expression tree processing application. Applying interpreter, which we talked about in the previous video, helped us to automate the parsing of user input expressions in order to be able to create a parse tree. We still have to determine, however, how to convert the input into an expression tree. One thing we don't want to do is hard code the interpreter to only generate a particular type of output. Since this is inflexible, it's limited in scope, we can only deal with certain sets of output, and it also precludes additional semantic analysis and optimization that we might want to apply in order to further improve the performance or other types of analytic properties of our ultimately generated expression tree. So what's the solution? We're going to figure out a way to apply the builder pattern to build complex objects incrementally. First, we'll have the interpreter create the parse tree, and optionally it can analyze and optimize this parse tree. And then we'll have a traversal of the resulting parse tree recursively to build the nodes in the corresponding expression tree composite. Note here that the expression tree representation may be very different from the parse tree, different ways of representing the information, keeping more information, less information, smaller information, etc. So we don't want to have to hard code those two trees to be related to each other. We want to keep them separate and decoupled as much as possible. The way we're going to do this is we're going to define something called the symbol class hierarchy. The symbol class hierarchy will be used to represent the nodes in the parse tree, which in turn are used to build the corresponding nodes in the expression tree. So when the interpreter runs, it's going to go ahead and create the various nodes, and all the nodes in the parse tree will be based on the abstract class called symbol. And that class has certain methods. It has a class method for dealing with the precedence. It has a method for also being able to build a component node that corresponds to the corresponding node in the parse tree. Here's how this actually looks from a visualization point of view. The interpreter will create a parse tree incrementally by instantiating subclasses of symbol. From a commonality and variability point of view, we're going to define a common interface for building parse trees and expression trees from user input expressions using our interpreter. And then from a variability point of view, we're going to be able to vary different ways of creating a mapping from the parse tree nodes into the expression tree nodes. This particular way of arranging structures and behaviors is given a name as one of the patterns in the Gang of Four book, and that pattern is called builder. The intent of the pattern is to separate the construction of a complex object from its implementation. You should apply this pattern in a couple of circumstances. One, when you need to isolate the knowledge of the creation of a complex object out of its constituent parts. Also, when you need to be able to allow different implementations of interfaces from an object's parts. When you want to be able to have different ways of being able to implement things even though you have a common interface. The structure and participants of the pattern can be described as follows, and we'll map these back to our expression tree processing app, as well as describing the generic elements described in the Gang of Four book. First, there's something called a director, which is really coordinating the way in which the parts are being built. In our example, this will be done by the interpreter class. Then there's something called the builder, which knows how to build a particular part. In our expression tree processing app, that will be the symbol abstract base class. And then there's a concrete builder, which is used to actually create concrete products. In our case, that will be the number, subtract, add, multiply, divide, etc. subclasses of symbol that are used to build the corresponding parts of the expression tree processing app. And the particular types of products we'll be building will be things like leaf node, composite add node, composite subtract node, and so on. These are actually the elements that form the different nodes in an expression tree. Here's a picture that illustrates the generic collaborations between the various parts in the pattern. The director is going to essentially be used to construct the various constituent elements by building them up piece by piece or part by part. And when everything's done, we'll end up with a resulting structure that's passed back to the client for further processing. So let's see how we could go ahead and apply the builder pattern in our Java implementation. The build expression tree method builds composite expression trees from the parse trees. As we saw before, that's done by the method in the interpreter class called build expression tree, which is going to take in a stack of symbols which have been parsed, and then it's going to go ahead and make the appropriate expression tree that corresponds to this particular parse tree. And as we'll see here, this works in a recursive manner. It simply takes a look at the top element on the stack, which will be the root of the parse tree, and then it will go ahead and recursively traverse down and build the entire expression tree from that point onwards. At every step along the way, we'll be transforming symbol subclasses in the parse tree, things like multiply or number, into the corresponding expression tree component node hierarchy. So as you can see here, the multiply class, which extends operator, which is a subclass of symbol, has a build method, which is used to create a new composite multiply node, recursively building the left tree and the right tree that corresponds to what's in the parse tree. At the edges of the tree are essentially the numbers. These would include things like the number 4, the number 5. These also extend symbol, and they contain a build method, and that build method in this case returns the appropriate leaf node parameterized with the value of the item in that particular number. That corresponds to the base of the recursion. Let's now go ahead and take a look at the actual code that is implemented in Java for our expression tree processing app, and we'll explore various ways in which this code implements the builder pattern. The builder pattern implementation also resides inside the interpreter.java file. If we go back and look at the interpret method that we talked about for interpreter, recall that there were 3 steps in the template method: build the parse tree, optimize the parse tree, build the expression tree. Optimize parse tree is just a no-op, so we won't talk about it now. If you wanted to actually implement it, you could inherit from interpreter and come up with a way to optimize and simplify the parse tree. Once that process is done, which, as we said, may be nothing at all, maybe a no-op, we now call the build expression tree method to actually build the expression tree. Let's go take a look at build expression tree. Build expression tree is quite simple. As you can see here, it's really just a one-liner. It first does an assertion check to make sure that the parse tree only has one element in it. That one element should be the root of the entire parse tree. And then we go ahead and we call the build method, which is a factory method from the builder pattern, on the root of the parse tree. And we take the result of that and we call make expression tree, which actually connects together the composite expression tree that's returned from the build method with the expression tree abstraction class from the bridge pattern that we talked about before. To understand how this recursive build process works, let's take a peek at how this might actually behave for an expression that we might have built up. Let's assume, for sake of argument, that we built up an expression something like 3 plus 4. So in that case, there'd be an add symbol at the top of the parse tree, and it would have a left child that would be a leaf node and a right child that would also be a leaf node. So when the build method is called, it's actually calling the build hook method on the add class. So let's take a look at that. Here's the add class. The add class has a build method, and what this build method does is it makes a new composite add node, which now we're in the world of the expression tree, no longer the parse tree. So it makes a new composite add node, and it recursively calls build on its left subchild and its right subchild. Now keep in mind, for this particular example, we're going to assume that we have leaf nodes for the left and the right child. So when we call left.build, that will end up going to the number class. And if you take a look at the number class has a build method, and the number class's build method creates a new leaf node, which stores the value of the item. And that's returned as a component node, of course, because that's the way the composite pattern works. So we'll get back a leaf node. In this case, it would correspond to a leaf node with a value 3, and then we'll also end up getting back a leaf node for the value 4. And so what would end up being done here when both of those recursive calls return, we'll end up with 2 component nodes that themselves actually point to leaf nodes, which are subclasses of component node. Those get passed to the composite add nodes constructor, and the composite add nodes constructor is then used to dynamically allocate a composite add node and that gets returned as a result of the build operation, which, as we can see back up here, is going to be returned as a new expression tree by the make expression tree factory method that returns here. So this is a nice example of how we can use the builder pattern to recursively and incrementally build up a complex object, in this case the composite expression tree, out of its building block parts, and by decomposing our interpreter into several phases. Phase number one we talked about in the interpreter video, where we converted the string into a parse tree, and then we took the parse tree and converted that into an expression tree. We leave ourselves additional leverage to do additional work, optimization, semantic analysis, and so on. And so even though our current optimized parse tree method is a no-op, it's straightforward to implement it to provide additional capability. Now that we've looked at all the code corresponding to the builder pattern, let's go ahead and evaluate the consequences of applying this pattern. There's a number of benefits that come from applying this pattern. One is to isolate the code for construction and representation. We can put that code in a set of places that are well defined and well understood. In our particular example, we put them into the various parse tree subclasses with their corresponding build methods. Using Builder also gives us very fine-grained control over the construction process. We can create things a little bit at a time, and we can do some kind of optimization if we so choose as we're putting the pieces together. You can also come up with ways to vary an internal representation of the product that's being produced without affecting the way in which the users of that product are affected. For example, we could come up with different ways to build our composite expression tree without changing the way in which that's accessed by the rest of the application via the bridge pattern. There are, of course, some downsides to this particular approach. They typically involve a lot of classes and a lot of class interdependencies. If you look at the diagram here, you see that there's many different relationships between nodes that exist in the parse tree hierarchy, in other words, the subclasses of symbol, and the corresponding nodes in the expression tree hierarchy, in other words, the subclasses of component node. Once again, knowledge of patterns helps to reduce the surface area of these many classes. So you can see the builder part, you can see the composite part, you can look at the forest as opposed to being overwhelmed by the number and complexity of the various trees, no pun intended. When you think about how to implement the builder, you can essentially view it as being some kind of factory with a mission. It goes beyond many of the other conventional factory patterns in the Gang of Four book, things like prototype or factory method or abstract factory, by allowing the behavioral steps to be embodied in terms of building a complex representation out of its constituent parts by connecting the various things together. So this gives you a more powerful way of being able to create things that belong together but are built one piece at a time. There's a number of interesting known uses of the builder pattern. It was also used in a number of Smalltalk compilers back in the day. It's used in parts of the ET++ user interface for doing conversions to a rich text format. This is something obviously Eric Gamma would have worked on as part of his PhD dissertation. An example of the builder pattern that's closest home for me is its application in the ACE service configurator framework, which is something I wrote many, many years ago. I actually developed this prior to being a reviewer for the Gang of Four book. And as I was reviewing the Gang of Four book, I was struck by the way in which my service configurator framework mapped nicely onto the various roles and responsibilities identified in the builder pattern. And in fact, the service configurator framework is cited as a known use in the Gang of Four book. I was using it in order to be able to build various parts of a small language for dynamically configuring applications and services out of building block components. And I found the builder was a nice way of being able to represent this, so I didn't have to worry about changing the implementations as I changed syntax or I changed various representations of the internal data. All that code is available in open source form, and there's also a paper you can take a look at as well to learn more about it. So to summarize the builder pattern, Builder recursively builds a composite-based expression tree data structure by processing the interpreter-based parse tree generated from the user input. As you see in this diagram, one of the powerful things about what we're doing here is we're actually combining together multiple patterns to form a pattern sequence. We're using interpreter to read the input in, convert it into a parse tree. We're combining that with Builder in order to be able to create an expression tree from the parse tree. And what Builder is creating is actually a composite. So these are examples of patterns that are chained together. As you start to get more comfortable with the Gang of Four patterns in isolation, you can rest assured that you'll also find ways of being able to combine together these patterns in ways that we're describing here, so that the context of one pattern is actually the output of a predecessor pattern that lines up in the sequence. This is a much more advanced way to think about the patterns. They work together, they solve larger problems, and we'll talk more about this as we get to other parts of the patterns in this discussion.